Thank you. The very first thing I wanted to do with you today was I forgot at the end of my last talk, after we were talking about the electromagnetic analogy for GR, I wanted to show you some things that we've been doing in our own research. Right? Hello? Right now, I'm working with a couple of students to try and model spinning sources that can actually. Okay, okay. We're trying to model spinning binary star systems, and you can use the gravitation or the electromagnetic analogy very nicely there. And so one of my students actually came up with this animation that shows two stars that are in orbit around each other, and they've got spins. And of course, because of the gravitomagnetic analogy, spinning stars will exert gravitomagnetic forces on each other. And there's also a spin-orbit interaction, so the orbits are carrying mass around in a circle. That creates a gravitomagnetic field to which both the spins respond. Now, the orbits here are so fast that I haven't bothered to try and model the stars actually going around in the orbit. You can just think of them whizzing around these circular orbits as quick as faster than the eye can see. But what this is modeling then is the actual spin and spin orbit interactions. And what it does, as you can see, the spin's precessing around, but also the total angular momentum of the orbit is precessing around due to those interactions. You can see this is getting faster and faster, and the orbits are getting smaller and smaller because energy is leaving in the form of gravitational waves. And the wobble of the orbital plane is going to affect the polarization of the gravitational waves and so on. But anyway, you can understand this all very nicely using the gravitomagnetic analogy. And while I'm on that, I will also say that, so this is my website that I gave you the address for. I can put it up again. But I've now put the slides for all the talks there. And in addition to the diagonal metric worksheet, I've also got the off-diagonal metric worksheet, which means a worksheet for when you have one off-diagonal component, as you have in Eddington-Finkelstein coordinates, for example, or Kerr. And so you can do the same kind of calculations. Of course, there are about twice as many terms, but you really can do it. So anyway, all right. So let's go to what I really want to talk about today, which is gravitational waves. And so what I intend to talk about, so I'm doing the very basics about gravitational waves. What's transverse-traceless gauge? Generating gravitational waves. Gravitational wave energy, that perennial problem of difficulty of dealing with energy in GR. Then if we have an idea of energy, how do I figure out what the luminosity of a source is? And then I'll end up with gravitational waves from binary star systems, which is the area of my research and also one of the most important sources for gravitational waves for our detectors. So let's begin. So we're going to pick up where we left off last time. We're going to take the weak field approximation, where we have a flat space metric and we perturb it just a little bit. We're going to define the trace reversed perturbation, where we subtract off the trace from the diagonal terms. Then the Einstein equation, as we saw last time, becomes this very simple equation. And we're also going to apply the Lorentz condition, Lorentz without the T, we're going to apply the Lorentz condition to that. So simultaneously solving these equations gives you the wave solutions. And remember that we have some remaining gauge freedom. So I can tweak the coordinates by a small amount, by a small function. This is a function of space and time. I can tweak it by a small amount, and it doesn't affect anything, the Lorentz condition or the solution, as long as the D'Alembertian of that perturbation is 0. All right? So, and just to remind ourselves also that the gauge transformation of the capital H looks like this. You take the functions that you're doing and add them to the original in this manner. Okay, so far? So in empty space, we're going to attempt a plane wave solution. And the Einstein equation, because in empty space I have nothing for the stress energy tensor, it just boils down to, so K sub alpha is a wave number 4 vector, and so it's got a time component that's equal to minus omega, where omega is the wave frequency, and then its spatial components go along with that. And what the Einstein equation, the only thing that the Einstein equation says is that when I take the derivative of this, I pull out a k sub alpha, and I take another derivative, I pull out a k super alpha, and those have to add up to 0. That's all the Einstein equation says. The Lorentz condition puts some conditions on the matrix. And we'll talk about those conditions later. And then I also have, just by nature of the symmetry of the perturbation, that the A matrix here, which is a constant amplitude matrix, has got to be symmetric. We good with that? So the Einstein equation implies that this is 0, and if I write out what that means in this particular case, and I'm using the flat space metric, and I take minus omega squared times eta sub tt is an overall minus omega squared, and then these three terms, and basically I get this out of that, where this is the magnitude of the spatial part of the wave vector. And that just says omega equals k, which means that the phase velocity is the speed of light. So that's what the Einstein equation says. In fact, the fact that omega is equal to k, if I took the derivative of both sides, I would see that the group velocity is also the speed of light. d omega is over dk is equal to 1. And so gravitational waves are going to move at the speed of light. Okay? So the real trick, though, is to tell, just because I get a solution of the metric perturbation doesn't mean I have a gravitational wave at all. It could mean that I just have a wiggly coordinate system on top of flat space. And how do I tell the difference between those? That was the problem that bedeviled people for a long time in the history of gravitational waves. And as Peter told you, it was Pirani who really focused on a path to the solution. Usually in gravitational, in GR textbooks, people will show you, oh, I can do this I can do this gauge transformation that actually erases most of the components, and I have a couple of components left. But how do you even know that the couple of components left mean anything? The only real way to do it, and I've actually never seen what I'm about to show you in any GR textbook. That doesn't mean it's not there, I just haven't seen it. But there is a more direct way to do it, which is akin to what Pirani showed, and that is to go to the Riemann tensor. The Riemann tensor is what tells you what's physically real in terms of curving space-time and what's just flat space-time in disguise. And so really what we have to do in order to determine what's going on is to evaluate. So here's the chart I had earlier. I've rewritten the indices to correspond to the current case. But here are the 21 possible independent components of the Riemann tensor. So if we evaluate all of these, then we will know what for sure corresponds to curved space-time and what is just flat space-time in disguise. And I've written the 21. There are only 20 independent ones because these three are related by one additional symmetry. Okay? So, and let's assume for the sake of argument that I've got a wave that's moving in the z direction. This is always done, but it's a really nice place to begin. So my k sub t is minus omega, my k sub z is omega, the other two components are 0. And then what you see is that the Lorentz condition puts some constraints on what the components of the amplitude matrix can be. So in particular, if I evaluate this for nu equals t, then I get that minus omega t ATT plus omega AZT is equal to 0, meaning that those two things have to be equal to each other to satisfy the Lorentz condition. And so if I evaluate that for nu equals x and nu equal y and nu equals z, I get more conditions. And then the symmetry implies that there are other relationships between there. So basically, a lot of these things that involve z's or t's in the as superscripts are going to be related. All right? So let's, and remember also that we have, well, I'm going to, in a minute, I'm going to evaluate the Riemann tensor, which involves double derivatives of the metric, the little h perturbation. So I want to put that in terms of the big H, and then in terms of my hypothetical wave solution. And I'm going to define this A as the trace of that amplitude matrix, which if you look at it is just going to be ATT minus ATT AXX AYY AZZ, but these two terms cancel because of the Lorentz condition. Those two terms are equal, so you're basically left with these two terms. That's what the trace is in this circumstance. And I want to remind you that if I'm raising or lowering indices using the flat space metric, if I raise or lower a time index, in this case if I'm going to lower time indices, if I do a time index, then I get a minus sign, unless I'm doing two time indices, in which you get two minus signs, which is a plus. Otherwise everything is positive. So it's not a big deal to go from taking my matrix in the upstairs format and lowering the indices. Most of the signs are the same. Okay, so I want to evaluate the Riemann tensor there for this case, and here is then the expansion. And remember that when I take a derivative, I pull out a factor of the wave 4 vector. And then I've got an overall sign coming out in the back. And I get an overall minus sign because cosine goes to minus sign. Are we good with this so far? So it's really just a matter of evaluating these. So let's look at just one. So the TX component. So remember the mnemonic? So inner togetherness is positive. So I take these two and I'm going to keep them together in the derivative term or in the other associated with the metric. Okay? Well, kx is 0. So this whole thing is 0. Kx is 0. That whole thing is 0. Kt, that's omega. So I get a minus omega squared. And axx minus eta sub xx is 1. So I subtract off the trace, which is just a sub xx plus a sub yy. And then these are 0. So the only term that matters is this one. And like I say, eta sub xx is 1. So I'm just subtracting off this. I basically get the difference between a sub xx and a sub yy. And what this is saying is that space-time will be curved if I've got a difference between those two components. So right there you know that at least you can have real gravitational waves. You've just got to make sure that these components are different. Okay? And you can evaluate other ones, and it turns out, for example, if you look at this one, and it's all in the printed version of my talk, if it looks like we're going to have something here. So gee, looks like those components matter too, but they don't. Why not? Anybody catch it? Why is that 0? Yeah, these involve x and t and x and z, and those are linked by the Lorentz condition. So they're opposite signs. So they cancel out. All right? So the entire list of Riemann components, if you work it out, now I won't completely vouch for all the signs because I was just working this out a couple of days ago and I haven't really had time to check them all, but I will verify that everything depends on either A, B, or is identically 0, where A is that difference between the AXX component and the AYY component, and B is related to the off-diagonal component. And you can also see that I've got the last symmetry condition that says basically that these three are related. And in fact, it specifically requires that if you rotate the last three index values, that adds up to 0. Well, I haven't got exactly those, but if I flip this one, then I have yzx, which is the right rotated thing. So I get a minus b here. Minus b plus 0 is 0. So we're fine. We're not getting any extra information from that condition. Okay? So this is actually easy to do, surprisingly easy to do. Doing the other kind of calculation where you actually do a gauge transformation to go and develop set all these components to 0 and see what's left is, I think, just about as hard. So I don't know why nobody, I haven't seen this in GR textbooks. But this is a very straightforward way. And the importance of this is that the other approach kind of, well, I'll get to that. It's clear that the only values that matter are the difference between these two values and that off-diagonal component. None of the Riemann tensors depend on any of the other components. And so we ought to be able to do a coordinate transformation that gets rid of all of those components because what the Riemann tensor is saying is that anything else is just a deformation of flat space-time. There's no physical meaning there. And so we ought to be able to do a coordinate transformation that erases everything with a time index and a space and a z index. And not only that, but we ought to be able to set the matrix to be traceless, because I can subtract a common term from both of these and it doesn't matter, it doesn't affect anything. So we call the gauge, so I'm assuming we can transform to a gauge, and if you want to see that, yeah, you can actually do this, look in basically any GR textbook. But we'll call the gauge where waves in the plus z direction have the form, so here's the traceless part involving this, and here's the off-diagonal part involving that. These are the two polarizations of a gravitational wave, and they're the only physically real parts of the gravitational wave. Everything else is meaningless. All right? So we call this transverse-traceless gauge, and the nice aspect of choosing the trace to be 0 is that then the little h is the same as the big H. And so our solution in transverse-traceless gauge for big H is also the solution for little h, and that makes things a lot easier. All right, we good with that so far? So part of why I like this approach for dealing with it is that when I was first learning about gravitational waves, I thought, oh gee, if I want to find the wave in a certain direction or something, I have to go through this very long process to figure out for each wave direction what the transverse-traceless gauge looks like. So I have to take my starting wave and do a complicated transformation. But you don't. And what I learned much, much later, and I'm trying to save you the effort of, is that you can just set those components to be 0. You don't have to go through some kind of complicated transformation problem. They don't matter at all. So just set them to be 0. Set the trace to be 0. You're fine. You're assured by this kind of calculation that you'll always be able to do that. So don't bother to go through all the effort of actually doing it mathematically. Just squash all those components. Make them go away. Yeah. 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 So I'm not doing that here. Right. So what you would have to do is go back to the original transformation thing. Where is it? No. Where is it? I know I had it here. I think it was at the very first. Yeah, here. Here we go. Okay? So what I need to do is find an epsilon, or a xi rather, function. And it turns out, yeah, you can define this xi function. It turns out that it's good if it's a 4-vector constant times a sine of the same sine wave of the same frequency as the hypothetical gravitational wave, and then you have enough conditions to determine all the b's that erase all your other components except the transverse traceless part. And you can do that, but and like say, look in any textbook, including my own, to see how to do that. But it's tedious, and this I think is clearer. Okay? Yes. Yeah. No, you can't do this in the strong field limit. In fact, the whole thing breaks down in the strong field limit. And there's not any precise way to do that as far as I know. I mean, because we're starting at the very beginning with with the weak field approximation and to get this equation. And if you're not in the weak field limit, then then this equation doesn't apply, and it's much more complicated. So I don't know personally, maybe somebody else knows about exact solutions in strong field limit, but I don't know personally how to do that. Yeah. Uh-huh. Yeah. Uh-huh. Maybe. Right. Yeah. And yeah. Yeah. Yes, you're absolutely right. I was thinking about our. Yeah, it is still. Yes. And no, it wasn't quite his question, I think, but yes, totally one can do that, and that's what I did for my PhD thesis. I was doing gravitational waves from stellar core collapse for supernova, and that's exactly what we did. We took a Schwarzschild background, we did perturbations on the Schwarzschild background, so it's weak modifications of the Schwarzschild background as opposed to the flat space background. But yeah, you can totally do that then. And then we propagated it out to the weak field, I'm sorry, to the flat space region and worked from there. So one can, in fact, do that. But if you really have strong perturbations where this doesn't apply anymore, then you've got to go to exact solutions or numeric solutions. Okay? Yeah? Uh-huh. There are, yes. Yeah. 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 There are a number of exact gravitational wave solutions, but not connected to sources, just that I'm aware of. Okay? So let's go on. So what does this wave do? Well, let's examine the geodesic equation. Geodesic equation is this, and I'm thinking about a mass at rest, so only the time component of its forward velocity is not zero. And I'm going to evaluate this in the transverse-traceless gauge using the definition of what the Christoffel symbol is. And I've got a time index here and a time index here and a time index here. Those components of the perturbation are all zero. So, whoa, wait a minute. That's saying that the waves have no physical effect? No, it does not say that. But this is an important step. What it says is that the transverse-traceless gauge, it gives you co-moving coordinates so that your floating masses remain at the same x coordinate or y coordinate And the coordinate system is wiggling along with your mass, as you might think about it in that way. So, and what have I been saying all throughout this? That the coordinates have no intrinsic meaning. You always have to go to the metric to find out what the coordinates mean physically. So let's go to the metric, and I'm going to actually evaluate the distance between my mirrors. And here, so I'm gonna say, let's have particles floating in a ring. This is sort of the classic way to demonstrate what a gravitational wave does. And my coordinate differences here are constant in my transverse-traceless gauge. So I'm just going to arrange them in a ring of constant distance in the coordinate and find out what the actual physical distance is. So I plug in what the distances are. This is the perturbed metric. This should have been a y squared. Sorry, I'll fix that. But it should have been a y squared. And then I'm just going to plug in what, think of delta x as being r times cosine theta. Delta y is r times sine theta. Plug that in. And I get this kind of expression, use a double angle formula to simplify that. And then what I did here was now I want to calculate delta S. And I had this. I'm going to take the binomial approximation. And I forgot a factor of 1/2 there that did show up here. Okay. But this is then the expression, and you can see from this expression that if I'm at 0 degrees, I'm going to get an enhancement of the distance. If I'm at 90 degrees, I'm going to get a decrease in the distance. And if I'm back at 180 degrees, I'll get an enhancement again. And for the cross-polarized wave, it looks pretty much the same, except that I've got a sine of 2 theta instead of cosine 2 theta. So, yeah, you got this classical picture. You've seen this a million times before. This is what a wave does to deform a ring of particles as it goes through, and then it oscillates back and forth. Okay, and the cross-polarized wave looks like that. And this is why the international symbol for dangerous gravitational waves looks like this. Right? Okay, sorry, that's a geeky joke. But because dangerous gravitational waves are kind of a contradiction in terms, we'll talk about that shortly. But, well, we'll talk about it right now. Let's generate some gravitational waves. At worst, a source will have a metric perturbation of order of magnitude 1. At the sort of Schwarzschild horizon, say we're coalescing two black holes, you're certainly going to have order of magnitude 1 perturbations. Now, the whole calculation breaks down at that point. We can't do anything with that. But let's just pretend that we could, and that there are real waves that are going off of that are amplitude, that the amplitude goes down as 1 over r. So take that first LIGO source, total of 60 solar masses, order of magnitude, which is about 100,000 meters. In terms, if you ask what's GM for that, is 100,000 meters. And the observed amplitude of the wave was 10 to the minus 21 at our location. So it must have been about 10 to the 26 meters away to go down from 1 at a radius of the Schwarzschild radius of the final mass to 10 to the minus 1 at our location. Does that make sense? And so that's about 10 to the 10th light years, 10 billion light years. The actual distance was 1.3 gigalight years. So this is an overestimate. I mean, this crude estimate is overestimating how good you get. But it gives you it's basically the right order of magnitude. And that's actually kind of a powerful thing. This is something that you can do with an introductory physics student. And this also says, let's imagine a kind of a worst case scenario for our own location. Let's say our sun has become a black hole and it swallows another black hole. The total GM for that is about 3,000 meters. So the wave at the Earth would be, here we're 1.5 times 10 to the 11th meters, compared to 3,000 meters is going to be smaller than 1 by this factor. Okay? So the gravitational wave that comes by us will change our length by a couple of nanometers. It'll stretch you and then shrink you by a couple of nanometers at our location. You think you'll feel that? Probably not. It'll completely blow the gaskets off a LIGO, but it won't do anything to you. So no such thing as dangerous gravitational waves. In order to really calculate what's going on, we need to do some more approximations. And the general approximation is called the small, weak, slow approximation. So we're going to take the source being small compared to both the wavelength and the distance to the observer. Now that's a terrifically good approximation for most cases that we're interested in. The source is weak in that we're going to assume that the perturbation is relatively small even at the source. Okay, that's a little tougher. That's certainly not going to apply to coalescing black holes, but it will apply to still a reasonable number of sources before coalescence, let's put it that way. And then the source is slow in that parts of the source move with speeds much smaller than light. That's actually also a pretty good approximation, except near coalescence. Okay, so weak means that we get to use the Einstein field equation even at the source. And that's the important thing. We know that the solutions to the Einstein equation are just the standard solutions to any D'Alembertian with a driving term, and it's just this. And S here is the distance to the source of a, so I'm integrating over points in the source, and I'm just saying what's the potential created by the point source, and I'm integrating over r vectors in the source, and this is going to change as I go to different places in the source, but this is the distance from the source point to the observer, and we're a capital R away from the center of mass of the source. Okay, so S is equal to capital R of where we are from the center of mass, and then the little r is from the source center of mass. We good with that? So small means that I can replace S by capital R. The source is so small that S is going to be insignificantly different from R during that entire integration. And so then all I have to do is integrate over this source, and I'm not even going to worry about the denominator. I've pulled that out. And this is what we then need to do to figure out the gravitational waves that come from that source. All right, well, there are, you can do those integrals. And the first integral is you find that h super tt is a constant. It's just gm over r. And the ti, where I is a spatial index, those are going to integrate to 0. And that's basically from conservation of energy and momentum. But what's interesting is the integral over the spatial components of the stress energy. And it turns out that there is a trick, a mathematical trick that you can do to convert this integral into an integral over the density times spatial positions and take the double time derivative. Now that trick is just math, and I did it in the printed version of this talk, but I'm not going to duplicate it here because it's just math and it's really tedious and it's lots of steps, but I'm happy to go over it with anybody who really wants to know. But this is a fantastic trick because this is basically the density times these positions, and that thing is the quadrupole moment tensor for your object. And so you're basically saying you take 2 time derivatives of the quadrupole moment tensor. That gives you what this integral is. And this depends on, it is math, but the only other thing that depends on is conservation, local conservation of energy and momentum. In other words, the divergence of the stress energy is 0. But this is a very powerful result because this is easy to evaluate for almost any kind of realistic source. And then what we're going to do is actually define a traceless version of this moment of inertia tensor. So this is called, quadrupole moment tensor. So this is called the reduced quadrupole moment tensor. And the nice thing about that is it's traceless. And so your gravitational wave in transverse-traceless coordinates is going to be the difference. The difference, that's the only physical part that matters. You can write that in terms of the source. 2's cancel out. No, but you want to keep it here because this is the part, this is the amplitude that matters. It becomes the XX component of the quadrupole moment tensor converted to transverse-traceless. This is the definition of what that means. Okay, and similarly, YY is this is the part that matters, and that becomes the definition of that transverse-traceless moment of inertia, reduced quadrupole moment tensor. Okay, and here's the off-diagonal component. So we've now connected the gravitational wave with our source, the physically important part of our source, and it's this quadrupole moment tensor. And I just want to say, I mean, it's actually pretty easy to see from an electromagnetic analogy why it ought to be the quadrupole moment tensor. Even in electricity and magnetism, you can't have monopole radiation exactly. But certainly in gravity, you're not going to have monopole radiation. Basically, that part is this constant part. You can't have dipole radiation in general relativity. Why? Yeah, there is no such thing as minus mass. So there is no dipole moment. So the only thing that can, and we know from the Birkhoff theorem that a monopole, even if you're expanding or contracting, both in electricity and magnetism and GR, cannot radiate. So the first thing that could radiate if you were doing a multipole expansion is the quadrupole. And so that all makes sense. All right? So, gravitational wave energy. This is such a hard topic for the reasons that I talked about to you before. We really can't talk very easily about conservation of energy in general relativity as a whole. But in this particular case, we can do a trick that satisfies all our intuition about how this ought to work. And so we can talk about gravitational wave energy being radiated and the source losing that energy, all the stuff that we want. It's basically because we have a flat space-time as a reference background. Otherwise, this would be impossible. So the trick is that the Einstein equation as we have it, this equation is the first order expansion of the Einstein tensor. And yes, not yet. As far as I know, I was asking myself the question too. I don't believe I have yet. Yeah, even for rapidly moving sources. Yes, yes. I think where the slow part comes in later, and I do hope to get to that. But yeah, I looked. In fact, I asked the same question myself when I was preparing this talk, because I had usually seen it all presented as a unit, but I looked over the derivation. The derivation for that quadrupole moment tensor simply depends on energy conservation and mass. There's nothing about slow there. Yeah, yeah, that's right. So then you no, it doesn't, because you have to add new terms to the quadrupole. Uh, oh, sorry. Sorry, I see what you're saying. No, I think, yeah, think the issue is that you have. Actually, I need to think about that, but I think I, I I think that you only need to use the approximation into what goes into the to calculating the quadrupole moment tensor. And usually people expand those terms apart, but it's just going into calculating the quadrupole moment tensor, I'm pretty sure. Yeah, 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 yes, I think that. Yeah, it's come. Yeah, no, that's a good question. Let me ponder that and think about it. But like I say, when you go over the derivation, which you can see in the printed version of the handouts I have, doesn't depend on any assumption of slow, as far as I could see. Yeah. Mhm. Yeah. Yeah. Yeah, but uh, yeah, no, but it doesn't matter because the rho, the density, for relativistic matter is different than the density it would be in a sort of a Newtonian approximation, but we don't care about that. Whatever rho is, that's what rho is. So uh, I don't think that there's any issues there. Anyway, let's ponder this a little later, but if I can go on. So the trick is that we're going to expand this. If you think about it, the gravitational field, people feeds back on itself because the field equations are nonlinear. And so if there's going to be any sense in which the gravitational field itself enters into this process, it's going to be in nonlinear terms. So the idea, the trick is to expand the left side of this to second order in the metric perturbation. And it's actually a subtle question as to why you don't need to do that to the other side, but basically the reason is that the only components that matter are the spatial components, and they're already really small compared to the density for Newtonian type sources. So there's a case where there is some issue in terms of calculating that we would probably, if we had speeds high as the speed of light, this trick wouldn't work very well because there would be terms on this side that we wouldn't get to neglect. But anyway, terms that we're going to accept second order terms here, and the Einstein equation, if I just rewrite it in a different way and move these terms over to the other side, make them part of the stress energy tensor. So I absorb them into the stress energy tensor, where I'm talking about this gravitational wave energy are the second order terms to the Einstein tensor divided by 8 pi g. And that gives you an energy, because Lorentz gauge says that the derivative of h mu nu is 0. Then I'm going to have this whole thing be conserved. Let me see that I... Yes, you're correct. This should be minus here. I think I've got it correct in some of the other places, but it should be minus there. Yep. Thank you. Okay. So anyway, we've got a conserved quantity, and because we're using flat space as kind of a background, we're really considering the parametric perturbation to be on top of the background. We can integrate this divergence over a volume and say, yes, the total energy inside this enclosed volume of space-time is conserved, and go from there. Okay, so the problems with this is that this is really only a tensor with regard to Lorentz with the t-type transformations. In other words, I can boost and I can rotate, but I can't, it doesn't even work. It's not even invariant under a gauge transformation. So this is not a real tensor. But it does work if you average over a few wavelengths. And the trick is that there are terms in it that give you trouble when you try to transform to transverse-traceless coordinates. But those terms average out to 0. So then if you average over a few wavelengths, then you get something that is invariant under that gauge transformation, and you can go on. Okay? So in terms of fundamental physics, this is not working very well. So I should have a minus sign here. So we're going to average over a couple wavelengths. All right, so let's figure out how to do this. So I'm going to consider a plus polarized wave. And I'm going to assume that. And the first derivative is the same as the negative z derivative. And you pull out an omega and a minus sign. Double derivative is the same as... Double time derivative is the same as a double z derivative, and it's negative across derivative, and it's minus omega squared times that. And you can use the diagonal metric worksheet to evaluate terms of the Ricci tensor. And so I showed you how to use the diagonal metric worksheet. It turns out for the Ricci tensor, time component, these are the only things that matter, and so here is your term. Now the first order approximation to the Ricci tensor is 0 because we're in vacuum space-time. Okay, so these are all going to be second order in the derivative in one way or another. And so you get an expression that looks like this exactly. But, so here's that same expression that I had at the bottom of the last slide, but I can use the binomial approximation to put these things in the numerator. And I don't need to here, I don't need to worry about these denominators at all because I'm already to second order. So I'm just keeping second order terms. The second order terms for here and here are the same, they add up to this. But the first order terms, if I use the binomial approximation here and I use it here, then the leading term involving just the h double dot goes away, cancels out, and I'm left with this is the second order correction. Okay? And now I'm going to average over a couple of wavelengths. So I expand out what this thing is, and the average of this part is going to be 0, but the average of this part is not going to be 0. And so I'm left with this, and that is then the RTT component. And you can do the same thing with the other components, and you'll find those results. It's not very difficult to do, particularly with the diagonal metric worksheet. So here is an example. So here is an exercise that you can do to test it yourself. I'll skip over that. So now the other question is, well, what is R to second order, the curvature scalar? And if you look at it, it's just 0. Okay? Yes, averaging over wavelengths, right? But that's not, that's not the reason it's 0. It's because HTT in transverse-traceless coordinates is 0. And equal to HZZ. Yes, it's from the previous thing, and RZZ is the same thing as RTT, and so they're all equal to 0. So now let's go back to the gravitational wave energy. This gives you energy density then as the time component, and here I've got the minus sign correctly, and so I'm evaluate it, and from our earlier result, it's just equal to that. So the effective energy density of a cross-polarized wave must be the same. It's a little hard to figure out with the diagonal metric matrix, or with the diagonal metric worksheet, I mean. But it's got to be the same just because it's 45 degrees rotated, so it can't be any different. So here's your total gravitational wave energy density, which I could write like this, where I'm summing over all those transverse-traceless components, and when I do that double sum here, and I'm summing over the spatial indices only, that's what the Latin letters mean, then I basically pick up 2 of these and 2 of these, and so that's why the 32 here. Okay, so the gravitational wave energy flux is technically this component, but we already figured out that that was equal to the TT component, so it's actually the same as the energy density. And see if you can tell me why. Why is the energy flux same as the energy density? Yeah, speed of light is 1. That's basically it. Okay? So to put it another way, I would measure energy flux in units of energy per area per time, but I'm measuring time in units of meters, so it's energy per meter cubed. Same thing as energy density. All right? So let's think about calculating source luminosities. The problem we're encountering here is that you have a different transverse-traceless gauge for every wave direction. I showed you how to do it in the z direction, but the question is, well, all right, if I'm going to calculate luminosities, I need to have waves going out in all directions, so I need to calculate what the energy flux is, what the transverse-traceless gauge is, and therefore what the energy flux is in all directions. Now, conceptually, this is actually not difficult. Mathematically, right? Conceptually, for a wave in a z direction, what we did was we took our perturbation, we projected it on the plane perpendicular to the perturbation. In other words, I erased all the t and z components, right? And then I had a set of 4 components left in the middle, and I subtracted half of the trace of the projected matrix from the two remaining diagonal elements to make it traceless, and then the other two are automatically equal because the matrix is symmetric. And so I'm done. That's all I did. Squash all the non-transverse components and subtract off the trace. So I get traceless. So, and we can think about, say, if I want to take, so let me say I have a matrix here with a bunch of components. So I've got A, T, oh, you can't probably see that very well. A, T, T, A, T, X, A, T, Y, etc., etc. So let me just put in placeholders for all those. So I've got this. Okay, say I want to do this in the x direction, for waves in the x direction. So what would I do? So the very first thing is that I project onto the YZ plane, right? So I'm gonna erase anything with a T and an X in it. Okay, so I've got 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Oops, too many zeros. There we go. And this is YY, and this is ZZ, and this is YZ, ZY. Okay? Now, and then I take these two, add them up, and subtract off half from each value. So I'll get something where I have AYY and minus AYY. And now I've got the transverse traceless for the x direction. That's all I need to do. Does that make sense? Okay, so the solution for doing this in arbitrary directions is to express these operations in terms of three tensors that give the correct components in any rotated coordinate system. So it turns out that the tensor projection operator that projects a vector onto a plane, this is a vector, onto a plane perpendicular to an n vector, a unit n vector is that. Okay? And when n is in the z direction, I've got the Kronecker delta, which is just the identity matrix, and I'm going to subtract off this thing. If n is in the z direction, it only has z components, and it's a unit vector. And so I get this projection, and you see if I multiply this by any vector, it's going to project it onto the xy plane. Okay? We good with that? So since the second rank tensor ought to behave like the tensor product of two vectors, the projection of a three tensor, a second rank tensor, is going to be like that. Two projections. And basically, in matrix form, you'd sandwich the matrix in between the two projection operators. So that projects you, and then the trace of the projected matrix ought to be, and you do a lot of calculations, and you have that projection operator multiplied times the trace, basically, multiply both indices. Operating on your second rank tensor. So to complete the transformation, if you want to go in any particular direction to get the transverse traceless, you do the projection and then you subtract off the trace. And that's it. Okay? So the energy flux of a gravitational wave is this. We also know from our earlier discussion about getting the source of that. So flux in a given direction is going to be the transverse traceless version of this, and I've pulled out the common factors out in front. And if you do lots and lots of work on this, for any arbitrary direction, the flux in that direction is this. Now, it's just tedious work, It's not complicated work, but you can do that. And it's actually in my textbook if you want to see it. Okay? So now to get the total luminosity, we just want to integrate over all possible directions. And the nice thing about, so we're going to integrate this beastie here over all possible spherical directions. The nice thing is that the quadrupole moment tensor, that doesn't depend on what directions you're looking at the gravitational waves. That's about the source, and it's about your coordinate system that you set up at the source. So it doesn't care. We can pull those kinds of terms out in front of this integral and just do the integrals over the ends. That's what matters. And this is just, each integral is just a number that depends on the index values, and you can figure out what those are. I have a homework problem on the printed version of the talk that you can play with that. The result is this, and this is very important. That gives you the rate at which energy is lost by the system as a function of triple time derivatives of the reduced quadrupole moment tensor. Yeah. Sure. It's got to be a triple derivative because my wave function is double derivative, and then the flux of energy is, according that second order approximation, is from the first derivative of that. So yeah, it's a triple time derivative, one of the few in physics that I know, which is why the question. It's a very odd thing. In fact, LaTeX, you have to go through a whole bunch of hoops to do a triple time derivative. It doesn't like it. So, but that is the result, and that's very important for a lot of the applications that we have. Okay? So, let's try and calculate gravitational waves from binary sources. So the fundamentals are that I'm going to take 2 point-like objects, one with mass m1 and one with mass m2. I'm going to go to center mass coordinates. I'm going to assume they're in a circular orbit, which is not really a great approximation for a lot of astrophysical sources, but the orbits will tend in that direction because even gravitational radiation is enhanced at the close part, the perihelion part of the orbit, so it tends to circularize the orbits eventually. But we're doing a simple model here. So circular orbits, I'm just doing ordinary Newtonian calculations. I'm going to calculate the Ixx for a system orbiting the xy plane, and it's just, if I just expand out what this is only non-zero at the 2 points, and so I get a total mass times the position of the 1 point, subtract off the 1/3 of the distance, the total distance for that object, and then do the same for the other object. You get an expression that looks like this once I've plugged in what these are, and so on and so on, and you can derive all the terms for this reduced quadrupole moment tensor. And then you can do some simplification. This eta is a very powerful unitless expression of the difference in the masses, and you also need the total mass, and you can re-express that. All this quantity, which looks complicated in terms of eta and m, and the distance between the objects, just becomes something simple. Okay? So our whole reduced quadrupole moment tensor becomes that, and I've taken the cosine squared and the other terms and used double angle formulas. That simplifies things too. So everything turns out, the reduced quadrupole moment tensor depends on 2 omega. And you remember something about that? The gravitational waves from a binary system have frequency of twice the orbital frequency. And that's where this is coming from. Okay? So then I take a couple of, so here's the same thing again, I just copied it over. I take a couple of time derivatives. And now here's the gravitational waves coming from that source. The ij in the transverse traceless is equal to the capital H, which we determined was equal to that in the transverse traceless. And here are all the components of the gravitational wave coming from that. Now, already, this is naturally in transverse traceless coordinates for the z direction of waves. And so really this step, I should have asked the question, well, what direction am I talking about? Well, if I just asked the question, what's the quadrupole moment tensor without the TT, it's this. But you can see that that's actually already in transverse traceless because the z components are all 0. I'm not even showing the time components. We're already there. And so, and you can see it's traceless already. And so I get a plus polarization and I get a cross polarization. They're equal amounts in terms of magnitude, and they're 90 degrees out of phase, which means what about this gravitational wave? What kind of polarization? If it were light, what would it be? Yeah, circularly polarized, yeah. So this is a circularly polarized gravitational wave if we're looking in the z direction. To find waves in another direction, we can project it or just do it by eye. For the x direction, I take that matrix and do the processes I was talking about here, and you get, it's purely linearly polarized. I'm sorry, not linearly, plus polarized. All right? And it's got half the magnitude, I think, if I remember right. Let me see. Yeah, half the magnitude. So if I'm looking at the x direction where the thing is edge on, I only get waves of one polarization, and they're not as strong. But you can do it in any arbitrary direction by doing that. And I have an exercise here that we've sort of basically already done. Questions so far? All right. So if you want to find the luminosity, you can calculate this quantity, and you can totally do this. It's pretty easy to take this thing and sum over, whatever in whatever direction you're in. Well, I'm sorry. We're just taking, the original, yes, this original quadrupole moment tensor, we're summing the components. I get cosine squared and sine squared. And so it's pretty easy to do that sum. Sorry. Still back one. So I get this expression for the energy loss. Now, the trouble is that I'll get to that in a minute. Yeah. So, yeah, here I had the original matrix. I'm just summing over the various terms. I get 2 terms from each side, so I get 32 instead of 16. But it's just this and expanding it. All right? The trouble is that this is really not the nicest form yet, because that expression involves both the distance and the omega, the orbital frequency, which I should point out, that's pretty cool. 6th power dependence on the frequency. That's an amazing frequency dependence. So you can see that sources with a given separation are going to radiate much more strongly if they're orbiting fast. But the tricky part is that these 2 quantities are actually linked. through the mass. So if you know the mass and you know the distance, then you know omega, or any two of those things will give you the thirds. So we really want to get rid of that dependence. So I'm going to do Newton's second law. The gravitational acceleration is equal to m times v squared over r. And you get that law, which should be familiar to you. That's Kepler's third law. And so now I'm going to use that to eliminate d. And so I get that the energy loss is equal to this unitless quantity, gm omega. Gm has units of meters, omega has units of inverse meters, so that's unitless, raised to the 10⁻³ power. Kind of a weird power, but there you are. And then there's a part that depends on how extreme the mass separation is. And that's your rate of energy loss. And this energy comes at the expense of orbital energy. And the orbital energy, this is a standard Newtonian form for that orbital energy. You just plug in what m1 and m2 are. It's going to be equal to that. And use that expression to eliminate the d. And you end up with that expression for the total orbital energy. And the interesting question to ask is, well, our whole approximation about circular orbits, is it going to fall apart if I'm spiraling in too fast? In other words, my orbits are not really circular, they're spiral. But as long as the spiraling in is not too fast, then it doesn't much matter. So one way of quantifying what too fast means would be to calculate the rate of change of the period with respect to time. And this is a unitless quantity, and I can calculate it by calculating how does the period depend on omega, how does omega depend on energy, how does energy depend on time. And I just pull, so here is energy as a function of omega, and so I evaluate the derivative and find out what that is. And then I'm going to plug that in here for the middle term. Here's the energy related to time that we just derived. And here's how the period is related to the angular frequency. And you end up with this expression. And all of these expressions are not nicely expressed in terms of these unitless quantities. So if you can figure that out for a gravitational source, you've really got the information you need. I will say that a different way of talking about this is to talk about the rate at which the frequency changes. That's not a unitless quantity, but so it's more complicated. But the interesting thing is that you can write that. Here I had an omega to the 11/3 because I'm not dividing by omega to the 6/3 the way I did before. So I have an omega to the 11/3 power, and then I have this gm to the 5/3 power left over, same thing as here. I ultimately had gm to the 5/3 power. But I can re-express it by absorbing the eta into the m and calling it a script n. So all I'm doing is absorbing the eta into the m. And so here is an expression, and you can see that the rate of change of the frequency, for a given frequency, it depends solely on that script m mass. That's called the chirp mass. Okay? And the whole point of the chirp mass is that it gives the rate of change of the frequency at a given frequency. So if you have a source at a certain frequency, you can connect this chirp mass of the source to the rate of change of that frequency. The more mass you have, more chirp mass you have, the faster the frequency is going to change. All right? So we can actually do this kind of calculation for an actual star in the sky. It consists, so this particular system is one of the Lisa verification binaries. It has a mass that's known, it has a period that's known, has a distance that's not so well known, but we'll make a guess that it's about 16,000 light years. That's 5,000 megaparsecs. And you can calculate the GM omega. It's like that. So the amplitude from this system is 1.3 times 10 to the 22nd. That's it's easy to see with Lisa if you integrate over a long enough time period. Lisa's noise curve will be well below that. And it's radiating 10 to the 28 watts, which is comparable to the energy radiated by the sun in electromagnetic radiation. That's a lot of gravitational wave energy coming off of that. And yet the rate of change of the period is basically 4 times 10 to the 11th, so 40 picoseconds per second. Okay, so it's not changing all that much. A lot of energy to radiate is what that means. All right? And you can verify these powers. This is something I have my students do all the time. Here's G in the units that I'm using, where I'm not setting G equal to 1, but I am using time in meters. And all you do is multiply out to get the expression you want, but then at the very end, if you want watts, multiply by enough powers of C to give you the right units, and you're done. It's really not that difficult to switch the units in this case. Okay, this is another piece of evidence, very well-known piece of evidence. This is the latest curve from Joel Weisberg, and this is the energy prediction. The solid curve is the energy prediction of the how the orbital period of this binary pulsar system would change, and compared to the actual observed values, and it's spot on. So before LIGO, this was the best evidence for gravitational waves that existed, but it's still awfully good evidence that this whole scheme that we've cooked up with taking the second order perturbations of the weak field and doing all of that yields the right stuff. Okay, so you can do, and this is actually the research work that I've been doing, you can do post-Newtonian calculations where you take that source, and here we're going to compute, I think what we're doing is computing the quadrupole moment tensor, but now we're taking account of the fact that our source elements are not necessarily moving with low speeds compared to the speed of light. So we're talking about orbiting binaries as they're approaching their coalescence, but not yet there. And you can expand it in a power series where your y is this factor, which is basically proportional to v squared. So y squared would be a v squared to the 4th term. And you can expand the gravitational wave formula that I've given you in terms of gravitational wave at 0th post-Newtonian order, 1/2 post-Newtonian order, 1 post-Newtonian, 3/2, 2 second post-Newtonian order. It's just a power series in the speed of the source. So it's keeping, so here is, I think, where the real slow approximation comes in. In the slow approximation, you just think that the wave is this. In the post-Newtonian approximation, you try to keep more orders, And so your lowest order in this expression, it depends on the inclination angle of the orbit, but your lowest order is just what we're calculating. It's proportional to cosine. This is the phase of the orbit. And about the first post-Newtonian orbit correction involves things that depend on the difference in the masses, and there's a subharmonic and a 3/2 harmonic. So instead of the base frequency, which is 2 times psi, you get a 3 times psi and a psi term. And so these harmonics can contain extra information about the wave. And so if your detector is able to see those harmonics, you get extra information about the source. And that's basically what I and my research group have been working on, is trying to figure out what that extra information is and how valuable it is. Is it worth really looking for that? So I have a computer program called LISA that is modeling this for the LISA detector. You plug in sources. Here are all the parameters that go into defining a source. And then it generates the gravitational wave from the source. It then simulates its detection by LISA as LISA goes around the Earth in 1 year, and then calculates the signal that comes out of that, then applies noise, and using an information matrix approach, we do parameter estimation then back on the original source to try and figure out, whether we're going to be able to pick out the science from the noise from this. So in this particular case, we've got a solar mass, 6 solar masses. Our uncertainty is basically 0. We really know that mass very solidly. We know the distance to the source to a couple of light years. We know various things about the orbital parameters, the inclination angle, the sort of polarization angle of the plane of the orbit. We also know its location in the sky to 2 billionths. If we're watching it for a whole year, you get Doppler shifting as you go around, and the amount of Doppler shifting also tells you how high you are in the sky compared to the ecliptic. So by watching the signal for an entire year and parsing apart all those effects, you can actually locate that source very precisely with just one detector. And that's very cool. It's because LISA is precessing around as it goes around the Earth. So this is the kind of research that I've been doing, and we're trying to add the spins. That's the latest stuff, but we're not solving for that right now because we don't know exactly that our code is good. But we're trying to reduplicate what I did before we added the spinning sources. So this is really interesting research in trying to add some complexity to our models about binary star sources. And this is all post-Newtonian calculation. Okay, so I think I want to say at the end that if we want to talk about where we're all coming from, this is all started with Einstein, and it's here's a picture of him in 1916, 102 years ago, when he was coming out with the prediction that there might be gravitational waves, even though he later was more dubious about it. But it all began with him. But almost nothing of what I've showed you today, or in fact during most of my talk, really is his work. He just laid the foundations, and people subsequently in that light cone that started with him are unfolding all these things that I've showed you. This was, I love general relativity. I think it's a wonderful, beautiful theory, but its beauty has been extracted by people working for decades on this. And you are all a part of that journey. I'm a part of that journey. We are heir to people who have gone before us, Pirani and Cecile DeWitt Moreau, and all these people who've made real contributions. So carry on. Do your part. Thank you very much. So I will say I'll be around the rest of the conference. Everything's posted. I'm going to tweak today's to remove a few of the errors. And so feel free to talk to me about any of this stuff. And there are all sorts of fun problems that you can work, and I'm very glad to help you with those. Thank you all.